All right, so thought I'd have the exams back today. But I have to rely on someone else because I don't have the software on my computer, so I was waiting for them. I didn't get them back until this morning. And I teach most of the day, and before handing it back, I want to get a chance to make sure that there was absolutely no issues. So I want to go through each one, make sure, for whatever reason that if someone had a different form, it didn't end up in the wrong pile right before I hand them back. So I'll probably have the grades up. I'll try to get them up after class, kind of before 6. I've started tentatively looking at them. I don't think there's any issues. Looks like the average is right around 70, which is a little bit lower than I usually want to see it. However, there's a couple outliers kind of on the bottom end. So I'll take a look at that. I don't think there will be a curve. If there is, I'll post an announcement about what that will be. If anything, probably just a couple points to kind of get that average to be right around a 75, which is where I usually like to see them, right, at the minimum. Okay. So I will try to get them up there on Canvas, like I said, before 6 today. If for some reason I get back to my office and I'm presented with something I have to do before I leave the building today, that might not happen until tomorrow morning. But 95% chance that they'll be up there on Canvas before 6 tonight. Okay. I'll also be putting up a Learn Smart just to kind of get things out of the way before we jump into material. I'll be putting up a Learn Smart assignment, which will be going over the stuff kind of where we leave off today, kind of leading us into like the next topic. So I'll expect that you have that. The due date will be set to be before we start class Wednesday. So I think it's actually already showing up on Canvas. Yeah. So that will be due before we start class on Wednesday. Once again, should take 10 to 15 minutes, kind of graded for just completion. I may tomorrow also get posted to connect the next Excel assignment. Obviously, we haven't really covered very much since the last exam, so I'm not expecting that you even necessarily start working on those tomorrow when I post them. But after the first two classes this week, you can probably start to get the first few parts of those assignments done. So I want to get them up early so that you have that ability to do that if you want to start working on them early. Okay. Other than that, are there any questions for me before we jump into things today? Okay. So, there you go. We left off, and where we ended on the exam was thinking about discrete random variables. Right? So these were things where we didn't know the outcome and we could only see the integers. So we're next going to jump into continuous random variables, which are basically, right, kind of a similar idea. It's an experiment. We don't know what the outcome is going to be. We know there's a bunch of different outcomes that we could see. It's just now we can see not only the integers, but any value in between. So, we've talked about examples before. It's very similar. We're just thinking about continuous variables. It's just now it's an outcome that hasn't been realized yet. Right? It's kind of happening in the future. So just like discrete random variables, these continuous random variables will have distributions, right? We can kind of graph them out, right? Before, those look like bar graphs because we can only see integers. And now we'll get something that looks, I don't know why I didn't do this stuff. Sorry, slightly bad. Not bad, not for you guys, other things. So we've got what we're thinking about is this variable x, and it can take on all these different values, and our y-axis is still kind of representing the probability we see this random variable take on those values. So we're going to have a density function that gives us this probability, just like before, right? If I want to know what's the probability I see 5 successes, and plug that 5 into an equation that spits out me the probability I see 5. Okay? The problem is we can only look at intervals with a continuous random variable. So the reason why is if we think about, let's say I had 10 possible outcomes, each one was equally as likely. We would have said the probability of every outcome would have been what? 10 outcomes equally as likely. The probability of any one outcome would be 1 over 10. We had 100. Equally likely, 1 over 100. If I think about a truly continuous variable, how many values are between 1 and 2? Going back to like some older math classes. How many values, if it's truly continuous, any decimal response can be seen, how many values are there between 1 and 2? An infinite number of values. Right? Now we think about, we're not just looking between 1 and 2, sometimes we're thinking between 0 and a couple million, right? So we've got an infinite number infinite sign from this angle apparently. An infinite number of possible outcomes that a continuous random variable can take on. So even if they were equally as likely, the probability of any one outcome will be 1 over infinity, which in the limit is 0. So I say equal to 0 here. Truly, it's in the limit. But the idea is that we can't actually find the probability of any one value. Okay? So this presents some challenges to us, right? Because I'm going to see something that looks like this for my density function if I try to graph it out. I no longer have bars because I can see any value for x. So it's a little counterintuitive. Let's say I'm thinking about height, right? If I say I selected someone at random, what's the probability their height is in between, I don't know, 4'9" and 4'10"? Not very likely. So if we think about, what would that be? 60 inches is 5 feet. So we've got in between 57, 58 inches, right? Well, these different values, right? Truly, if we measure height to whatever decimal we wanted, it's saying that as we start to approach probably whatever the mean is, I think the mean is probably like between, if we just lumped all genders together, it's probably like 5, 6 or something. Right? The probability we see something in this range is going to be much less than if we looked at the same interval, but thought about what's the probability someone's in between 6'8" and 6'9", 6'8" and 6'9", 5'8" and 5'9", right? Well, those probabilities are much higher, right? So we've got to think about, we can't find the probability of any one value, but we can find the probability between for any interval. And we don't have to keep these intervals at a unit of 1. We could think about, I don't know, 72 and 72.01. We can make these really, really small. Right? So even though I can't find the probability of any one value, I could break this down and think about there's really like, this kind of looks like calculus probably, right? Really infinitesimally small rectangles under this curve, right? So what has to be true about whatever density function gives us our distribution is a couple things. So we've got this probability density function f of x. It's going to have a couple conditions, and they're really similar to what we were doing with discrete variables. So first of all, we can't see any sudden jumps. Okay. So everyone okay if I kind of erase this? Wasn't super important for you to kind of be copying. I'm just trying to give you a visual idea. So I'll show you some things that our density function can't do. What it can't do is when it gets to a certain value, it can't jump, right? So it has to be that it's true, like if it was to do something like this, it would still have to kind of keep this nice continuous line. We can't see any jumps, okay? The second thing, and I kind of already alluded to this, but if it's a probability, what's the lowest it could possibly be? 0, right? So in a really weird scenario, which we're not going to deal with any, but it could be that maybe this starts out here, goes down to 0, and then goes back up. It's not very likely we see something like this, but that's the craziest thing. Because if it ever dipped down below 0, well, how can we have a negative probability of being within a certain range? The lowest that probability could be is 0. So it's got to be at least 0, and we can't see any jumps. And I usually draw it out like this bell curve, because starting even today, but mostly Wednesday from Wednesday for the next couple of weeks, we'll be dealing with something called the normal distribution, or kind of sometimes called a bell curve. And so I usually draw it that way because we'll be using it a lot. Now, the other principle that we have, we think about those infinitesimally small rectangles underneath this curve. Well, if I was like adding up the probability of being in all of these different tiny intervals, and I added up the probability across every possible outcome, what should adding up the probability of every possible outcome get? 1. Right? Just like with discrete random variables. The only difference is here, we've got this nice continuous line. So what we're actually saying is the area under this curve is going to be equal to 1. And mathematically, that would mean if we went from the smallest to the highest possible value, and we integrated whatever that density function is, should always be equal to 1. We're just finding the area under the curve by doing that integration. Now, I'm not going to make you do any integration in this class. We're not going to like go heavy into calculus here, but that's the idea behind what we're doing, right? And I'll mention occasionally like integration. I think today we'll even get to this fact that we actually have a table we'll start using where someone else has already done the integration for us, right? It makes our life a little bit easier. So yeah, so really the same thing we were doing with discrete random variables. Excuse me. What I have here is the one that has area. So we already talked about the area under the curve is 1. And now I want to start thinking about, okay, we have this density function, but in practice, what we're going to actually use is a cumulative density function. So the cumulative density function is going to operate very similar to when we're doing cumulative relative frequencies. Okay. So I think I've got this in the slides, but I think I've got better visuals I can do here. So let's think about. Got some distribution. Let's say I'm interested in value A, and maybe the lowest possible value I could see. If I'm using this cumulative density function and I'm writing it kind of capital F, that's my cumulative density function. Whatever value I plug in for X, that function will tell me the probability that I see that value or anything below it, which is really just taking these like really, really infinitesimally small intervals and adding them all up. So if I use that cumulative density function, it's going to give me the area under the curve below whatever value I'm plugging into that cumulative density function. So to get this area here, we would say we write that as capital F of A. Questions? Is that clear? Any questions on that? So I can start to find the probability that I'm below certain values using that cumulative density function. What if I then wanted to find the probability I'm above a certain value? We'll call that value B. How could I use that cumulative density function to find the area to the right and underneath the curve of a certain value?
1 minus that.
Yeah, right. If I think about it, if I were to use that cumulative density function and plug in that value for B, I'd really be finding the area to the left. Well, if the area under the curve is 1, then the area to the right would just be 1 minus that. And what we're really saying there is if this is my event A, right? If you think about maybe this was the probability that X is less than or equal to, I don't know. Well, we could use B. Right? I'll put a value to it. Makes a little bit more sense. Let's say 10. Well, then the probability of being less than or equal to 10, the area to the right would just be the probability that X is greater than 10. Right? So all I'm really doing over here is finding complement. So the complement rule is kind of hidden behind the scenes there, right? I think the visual makes it a little bit easier. Like if I'm finding this entire area to the left of B, well, the area to the right, if the area under the curve is 1, has to just be 1 minus that. We're kind of exploiting the fact that we know the area under our curve for a continuous random variable will be 1, and that these two things, A and A complement, would have to add up to 1. Yeah.
Could you give A like a value to show?
Yeah, so we don't have an actual function here, but it'd be like if this was 5, we would plug a 5 into that cumulative density function. What that's really saying is, what's the probability this random variable X is less than or equal to 5? Now, this cumulative density function is really just, what's the probability X is less than or equal to that value? Does that help a little bit?
So when you're finding B, how would you relate the 5 to when you're trying to find B or trying to find?
Yeah, so let's say that B was 10. Right? So really what we're saying is, if I plug 10 into that cumulative density function, it's going to tell me the probability X is less than or equal to 10. So it's actually going to give me the entire area to the left. If I wanted to probability X is greater than 10, well, I could use that cumulative density function plug in 10 and then just subtract it from 1, right? Because then I know this was the complement of the original event A, if you want to think about event A that I was looking at. Does that help?
Yeah.
Any other questions on this? So I think I've got the slides, I've got some coming stuff. I'll return to this in a second. All right. So I just want the probability of seeing something less than A. I'm just plugging A into my cumulative density function. I want the probability that I'm greater than B. Well, that would just be 1 minus that cumulative density function when I plug B in. So if this cumulative density function is capital F, it's just telling me the probability of seeing a certain value or anything below it, then one of the traits of this cumulative density function, I'll do it over here, will be that as I get to really, really high values of X, actually, I'll start with the low values first. If I'm looking at really, really low values for X, the probability of seeing those values or anything below it, that probability is going to be relatively close to 0. Right? It's going to be pretty small. As I start to put in higher values into that cumulative density function, well, think about it this way. What if this distribution stopped at 100? 100 is the highest possible value I could ever see this variable take on. So maybe I'm thinking about like a test score, right? And this is the highest possible value I could ever see. So if I say, what's the probability that I see this student I selected at random get 100 or lower? That covers every possible grade that student could have got, right? That probability, that cumulative density should be 1. Right? So as I get to really, really high values for X, my cumulative density function gets really close to 1. For really, really small values of X, my cumulative density function gets closer and closer to 0. And that's really the same properties we talked about with that cumulative relative frequency. Okay? So it's really just kind of what we're doing with relative frequencies, but for an outcome that hasn't been realized yet, right? That's going to happen in the future, or that we're trying to predict kind of future outcomes. Any questions on that? Okay, so a little bit harder one. Okay? Let's say, I lost my red marker, so you'll have to go perfect. So let's say I want probability that I'm in between two values. How could I use that cumulative density function to find the probability that I'm in between A and B?
Use it first do f of b, find that, and then subtract f of a from it after you find that.
Yeah, here, let me use my color. I wanted to find that cumulative density function, whatever value b I'm interested in. It's going to give me the area under the curve, but to the left of b. Right? If I then use my cumulative density function, like we said, but I plug in that lower value of a, well, it's going to tell me the probability I see that x variable take on the value of a or anything below it. So if I subtract out, right, if I take that blue area and I subtract out this purple area, what am I left with? Well, that purple area kind of cancels everything out there with the blue area, so I'm just left with what's in between, or where those two areas don't intersect. Right? It's like I'm almost like I'm subtracting out the intersection. Right? So if I think about if these were actual values, and I said, okay, what's the probability x is less than or equal to 10, and the probability x is less than or equal to 5. Well, if I subtract out the probability x is less than or equal to 5 from the probability x is less than or equal to 10, I'm only left with the values between 5 and 10, right? Which is what I originally wanted, right? The probability I'm somewhere in between these values A and B, or like I said, 5 and 10 were the examples I was going. So we can use this cumulative density function to not only find the probability I'm below a certain value, above a certain value, but also the probability I'm in between two values. Any questions on that? So what if I wanted the probability, ignore it's on the screen up there for 1 second. What if I wanted the probability I'm in the tails, right? Less than A or greater than B? Well, using what we had from the previous slide, if I can find the probability I'm in between those two values, well, if I just subtract that from 1, I'd be left with what's outside of those values. But another way of thinking about that, since we have it up here, if I were just to take the area that's in this tail and add to it the area in that tail, that would give me what I want up there. Right? So what's over here? Well, that's just f of A. What's over here? We said earlier that's 1 minus f of B. If I add these together, what I end up with is 1 minus f of B plus f of A. And if I rearrange this, flips the signs, which is actually what I would have been doing before, right? Just subtracting this from 1 and would have given me what's in my tails. Now, in practice, we're not going to have to go through all this, right? Usually in practice, what we would do is just find the probability I'm in between A and B, and then just subtract it from 1. Right? But this will make a little more sense when we start working with actual functions, right? Actual cumulative density functions. But really, fundamentally, we're just finding different areas under this curve. And then sometimes we have a little bit of math here. We have to subtract something from 1. We have to add 2 areas together. Right? But fundamentally, we're just looking for different areas under the curve. Right? And we're kind of exploiting the fact that we know if we break this up into different areas, all of them have to add up to 1. Right? The entire area under the curve has to be equal to 1. Okay? We won't really use this cumulative density function notation too much. So if that's getting a little confusing, once we start working with the normal distribution, this will become a little bit easier probably than what we're doing right here. This is very like theoretical kind of math, right? We're writing things in all letters, But I want to kind of set us up before we get to working with some actual values, kind of what we're thinking about visually. All right. So any other questions before we kind of jump into the next thing? All right. So I will try to give you a lot of visuals today because I think it's important. And this probably says a lot about me, but I was listening to someone talk about, some Stanford professor talk about how to teach, not even teach really, it was how to think about mathematics and how you should always have a visual. You should never just be dealing with numbers. You should always be able to draw something in your mind. So I'll try to exploit that a lot today. So we were talking about just in general a continuous random variable, right? But we, just like with discrete random variables, we have very specific types of continuous, right? We have the binomial and the Poisson for discrete. What we're going to focus on today is the uniform, and then probably just introduce and start working on something called the normal distribution. Okay? So the uniform distribution, think about, we've got different values for x, and the probability kind of here on that y-axis. We can't find the probability of any one value, right? The probability of any one value we said earlier was 0. But we can find the probability over intervals. So for the uniform distribution, it's this unique type of variable where every equal sized interval has the exact same probability. So if I'm looking at the probability of being between 1 and 2, that's going to have the same probability as being in between the values of 7 and 8, right? Both intervals of size 1, right? They're 1 in length, right? They should have the exact same probability. So what's that going to look like when we graph it? Well, we're just going to be at the same point. If I can draw this above the numbers I wrote down. we're going to be at that same point on the y-axis. And if I look at, what's the probability I'm in between 4 and 5? Same size interval, so it has to have the same probability. So basically what we're going to end up with a uniform distribution is a rectangle, right? Now, where does it start and stop? We're going to call the minimum and the maximum value, kind of the way that we'll see this notation-wise when we look at the uniform distribution anywhere, like you look it up, is going to be, we'll call the minimum C and the maximum D, right? If it's easier for you to think about it, excuse me, D will be the max, C will be the minimum, and I'll kind of write it both ways. So even though I know that the same probability for every equally sized interval, if I could break those intervals into size 1, right, then it kind of goes back to what we were talking about before. Think about if I could see all the outcomes in between 0 and 10, I could break that up into 10 intervals of length 1, right? And each interval would be what? 1/10 of the entire distribution. So if I want to break this up into any size interval, not just an interval of length 1, I know that the probability of an interval of 1/2, right? Well, if I had intervals of size 1/2, there would be 20 of them in between 0 and 10. Right? And the probability of any one of those half-size intervals would just be 1/20th instead of 1/10. So the way that we can find the probability of any sized interval is just taking 1 over the range, right? And then multiplying it by however wide that interval is. Notice when I said it went from 0 to 10, 1 over the range there would be 1 over 10, and intervals of size 1 would have probabilities of 1/10. Intervals of size half would only have a probability of 1/20. Okay? And I'll show you another example, another way to think about that here in just a second. So another way of writing this would be 1 over D minus C, right? Or in this example, right, if I said the minimum was 0, the maximum was 10, 1 over 10 minus 0. Okay. So it then becomes a little bit easier if I think about the visual that I have here, which is, let's say I want the probability of being in between, I don't know, we'll say 1 and 3, right? So I want the probability that I'm in between these two values, but under my curve. Here, my curve doesn't look like a curve. It's just a flat line, but it's still my density curve. So if I want the probability I'm under the curve, but in between those two values, what shape do I have there? I know I'm not perfect at drawing, but what shape do I have here? A rectangle, right? So how do I find the area of a rectangle? Length times width, or sometimes you might see it as like base times height, right? So I always know the height of my rectangle because I know it's just 1 over the range of possible values. I also know the length of my interval. If it's going from 1 to 3, the length will just be 3 minus 1, right? It's the range or the range of values I'm interested in. Okay. Well, from there, it's just going to be take that width, multiply it by the height, and that would give me the area of that rectangle, which represents the probability I'm in between those values of 1 and 3. Okay. Write that out slightly differently over here because our actual density function is going to look something like this. Now, we can plug in our values here, and I'll kind of let you know what each one of them are. But D and C represent my max and my minimum. B and A are just going to represent the maximum of my interval I'm interested in and the minimum of the interval I'm interested in. So if I had something like this, and I think the example will run, let's say whenever I go to the BMV, I have no idea how long I'm going to be there, right? Sometimes I'm there 2 hours, sometimes you can be there like no time at all, walk in, walk out. So let's think of that as a uniformly distributed variable. We know the height will be 1 over that range. Or in this case, 1 over 120 minus 0. Let's say I want to know, okay, what's the probability that if I go there today, I wait somewhere in between 45 and 60 minutes. So I'm looking for that area. Well, I could plug all my values in, right? I could plug in, here's the beginning and the end of my interval, here's the minimum and the maximum of my uniform distribution. I can go ahead and plug those values in and say, okay, I've got what? 120 minus 0. Nope. That's my denominator. 120 minus 0. And I've got my A and B values are 60 minus 45. And that would tell me the probability I wait somewhere in between 45 and 60 minutes. Now, intuitively, if we look at this, right, the numbers I chose here are a little bit more difficult. But if I've got 120 minutes as the possible values I can see, and I'm looking for what's the probability I see X take on some value in between 45 and 60, well, that's just 15 minutes of the possible 120. So 15 over 120. That's all we're really doing. We're just thinking about how wide is this range of possible values? That's my denominator. And then the interval I'm interested in, well, how wide is that interval? Okay, so it's 15 out of the possible 120. Well, that's my probability. And that's only because everything is equally as likely. Another way of doing this is just thinking about, well, I'm looking for the area of a rectangle here. I can think about the height is always going to be 1 over my maximum minus my minimum. So that's the height of my rectangle. The base is always going to be the difference in between the maximum and the minimum of that interval I'm interested in. Well, if I rewrite this a little bit, I have exactly that density function. It's just, in my opinion, if I draw this out, it's a little bit easier to think about this as the area of a rectangle, right? And kind of labeling my points, maximum, minimum, and kind of the maximum of my interval. But really, it's like, almost like I said, you can think of it as I break this down, I've got 120 different possible minutes I can see, even though I can see anything in between 1 and 2 minutes, it's still, we can think about like 0 to 120 minutes. And the only outcomes I'm interested in are the ones that are between 45 and 60. Well, those are only 15 out of the 120 possible minutes. So there is some like intuition I think is like easier than actually like having to use all these equations when we're thinking about the uniform distribution. But the fail-safe is we use these equations, we'll always make sure we're thinking or our intuition is always operating correctly. But sometimes people come, well, why are we using all these equations? Like if I look at this and I know be anywhere between 0 and 120, right? And I'm only interested with a length of 15 out of those 120. Well, then the probability would just be 15 over 120. Right? And that's fine too, if that's the way you want to think about it. The visual kind of connects with your mind that way. You don't have to worry about kind of going through all the formulas, but you want to, you can. And I always think that the fail-safe way and the easiest is to draw this out, and then you're just thinking about finding the area of the rectangle. Questions on? We'll try to present it a couple different ways. So the next thing we'll talk about here. Well, before I show it to you, because I think that if I don't show it, it's fine. Let's say I've got a uniformly distributed variable. And I'll show you an easier one and then a more difficult. I'll draw these kind of quick here. So let's say I have a uniformly distributed variable, and I can only see it take on values in between 10 and 20. If everything's equally as likely, what should the mean of this distribution be? Anyone have any kind of intuition behind what the average value I would see for this variable be? I think someone said it. No. So if I can see any value between 10 and 20, they're all equal 15, right? So what you were really doing there was just finding the middle value in between that maximum and minimum, right? If you want to think about it, we could do this as a weighted mean. Take every possible value for X, multiply it by the probability I see that value, Now we could have to do that in like infinitesimally small intervals, but everything on either side is equally going to balance each other out. So all we really have to do is add up our minimum and our maximum and divide by 2. Right? So our equation for that mean is just take your maximum and your minimum, add them up, divide by 2. That would give you your mean. What ends up being true about the uniform also, because everything's equally as likely, it's a symmetric distribution. If I fold it in half around that mean, it's going to exactly fold on top of itself. So that would mean the mean is also equal to the what? The median, right? It exactly splits that data in half, 50% on the left, 50% on the right. Okay? So if I think about this way, like the probability I see something above the mean or below the mean are both 0.5. Okay? Now, the only other place where you can get tripped up a little bit, I think, is let's say I have a uniform distribution and it goes from 10 to -4. What would my mean be there? Yeah, so if I add up those values, divide by 2, I have to remember to kind of keep that negative sign, right? And so if I'm kind of adding these up and dividing by 2 here, 6/2 is 3. Now, sometimes people kind of forget, they just look at the value, so, oh, 10 plus 4 is 14, divided by 2 is 7, so that mean is 7. And this is where if you draw it out and plot that mean, you're going to go, wait, I'm supposed to be finding the middle values exactly in the middle. 7's a lot closer to 10 than it is to -4. I must have made a mistake. Sure enough, oh, I forgot the negative sign, right? So I go back, make sure I include that negative sign, and I'd find that mean of 3. Any questions over for either of those before we keep moving? So that one's kind of intuitive. The variance is not. The variance for a uniformly distributed variable is going to be equal to the range of possible values we could see, right? So maximum minus minimum. That goes back to that measure of dispersion, the range we talked about. Square that range of possible values and then divide by 12. If you want to Google search uniform variance mathematical proof, you can. Basically, the reason why this always will simplify down to this equation is, what we would really be doing is taking every x value, subtracting the mean, squaring that, right? Multiplying it by the probability, the probability of seeing that, which you can kind of think about, we would have something similar to, right? Our density function. And you can kind of walk through the proof, and basically it always boils down, it always simplifies down to the range squared divided by 12. So once we have these equations, it's relatively easy to figure out what the mean and the variance of a uniformly distributed variable is.
So the 12 is always going to be a given.
12, it's always going to be 12. So it's kind of like, you can kind of imagine, like, I've got something here squared, but it's also down, it's something similar is down here. So if I rearrange things and try to incorporate this, maybe I get it multiplied by 2, right? So it's that, like I said, you can walk through the mathematical proof. It's not overly interesting, but it always will simplify down to the range squared, and it's always just going to be over 12. So, any other questions? And then if I want the standard deviation, that should just be what? Take the square root of the variance. Right? It's the exact same thing as the variance. We're just taking the square root. Okay? All right. So we're kind of okay. Yeah.
So the population, so like the sample or population doesn't matter.
Doesn't matter here. So when we talked about sample versus population, we are coming at this. We're coming at this as though these random variables, we're always thinking about those as the population. We will probably next week start to talk about, okay, if we know the original variable, this population, if we want to think about it as, is distributed this way, but all we have as a sample, we start to run into some other issues. Okay, so that's kind of what we'll go over next week. But yeah, for now, you can think about these are all population random variables. Yeah. Any other questions? All right, so kind of see how well you were actually understanding. Okay? So let's say I've got this movie, right? And Mr. Nanny, to which there is an original movie. If you haven't watched it and you love like cringy old 80s movies, you should. It might be early 90s. It's a great Hulk Hogan movie. But let's say we're thinking about there's a movie theater, they're going to put on this new movie. They know the demand for popcorn is somewhere in between 1 and 10 pounds, but it's all equally as likely. It's hard to predict, but seeing demand be somewhere in between 1 and 2 pounds is the same as seeing it be in between 9 and 10, right? Every interval is equally as likely. So we've got the minimum is 1, the maximum is 10 of our uniformly distributed variable. So we could probably draw this out. I would suggest doing that. That would probably help. And then think about, okay, where's that mean pounds of popcorn that's going to be demanded? Okay. So give you a little bit of time to work on that. If you want to talk to the people next to you, go ahead and do that. And then in about a minute, we'll probably kind of talk about it and go over it. So we're just looking for the mean demand. All right. If you haven't gotten an answer in, take your best guess here. I'm going to close it out. Okay. So everybody got an answer. I'm going to close it out. We got 27. I think that's actually, I thought I counted 28, but so make sure you got an answer. I'm going to close it out. Okay. So what should this answer be? So 5.5. So how'd you come up with that?
B plus C over 2.
That's all it is. And what do D and C represent?
The minimum and the maximum.
Exactly. Perfect. So we are going from 1 to 10. All right. We're just going to add up those two values, divide by 2. We get 5.5. Now, common mistake I see here is for the variance, we were discussing the range, right? And for the height of this distribution, we were discussing the range. So if you instead took the maximum minus the minimum, you would have had what? 1 over, not 1 over, sorry. You would have had 10 minus 1 over 2. You would have gotten 4.5. But if you kind of plotted that point and you thought about it, well, 4.5 is a lot closer to 1 than it is to 10. So you should have known what? That number's not in the middle. I did something wrong. Sure enough, you go back, oh yeah, I didn't need the range. I just needed to add up that minimum and maximum value and then divide by 2. I'm just finding the average of the minimum and the maximum. That's all I'm doing there for the mean. Okay. Any questions on that one or any confusion you want kind of cleared up before we keep moving? All right, so remember, we want to find the probability I'm in between two values. We know the height of the distribution, that is going to be 1 over the range, 1 over the maximum minus the minimum. Okay. We then said, okay, if I want the probability being between two values, I just take the difference in those values, the width of my rectangle, multiply it by the height of that rectangle, and I'm done, right? Just find the area of a rectangle. Okay. So let's say you've got the same setup, but I now want to know what's the probability I see demand be greater than 9.5. So I think the way that this is phrased is the theater makes 9.5 pounds of popcorn. What's the probability they don't make enough? Well, the only values for which they wouldn't make enough would be anything above 9.5. But where do we stop? Well, the maximum value we could ever see is 10. So essentially, what I want you to find here, once again, work with the people around you, kind of work together here. What's the probability I see demand in between 9.5 and 10 pounds? Okay. So you want probability in between 9.5 and 10 pounds. Same kind of setup. Your minimum and maximum value of your uniform distribution is still 10 and 1. Okay. So give you a little bit of time to kind of work on this one. Like I said, I would draw something similar to this and kind of remember some of the things that we talked about. Going back, just as a reminder, the height of that distribution, remember, is just 1 over the range. Similar example with different numbers kind of over there. All right, we'll go to 2 minutes, 30 seconds here, and we'll talk about this one. So if you haven't gotten an answer in, take your best guess here at 27. I think that was the same number we had before, right? All right, I'm going to close it out. So also, when I showed this screen, sorry if I alarmed some of you, this is an actual footage from the movie, so I'm not making this up. So we want the probability it's in between. Essentially, we want it greater than 9.5, but we know that it had to stop at 10. So what would the height of this distribution be? Yeah, 1 over 9. So how did you get that? You took 1 over the maximum minus the minimum, or 1 over d minus c, or 1 over 10 minus 1, which gave you that height of 1/9, right? So we're kind of thinking about where the height of this distribution was 1/9. What was the length of your interval? Well, it started at 9.5, and it has to stop at the maximum, right? So if you think about the width of your interval here, it would just be 0.5 or 1/2. So you take the height, multiply it by the width, right? You end up with what, 1/18, which is, I think, 0.056 or 5.6%. Yeah.
Could you just do like 10 minus 9.5, 10 minus 1?
10 minus 9.5. Yeah. If you could, if that's easier for you to think about, that's the that is the actual density function, right? So yeah, you can just plug it into here, but really we said that's the same as taking the height, multiplying it by the width of that interval. Whichever way is easier for you to think about. Like, man, I really geeked out listening to this podcast this morning, but this was one of the points they made is exactly what you're saying. Like, there are different ways of like we think of math as like there's one way to do everything, right? Well, there's several ways to approach this, and they're all correct. Like, if it's easier for you to think about the area of a triangle and first find the height and width, it's easier for you to plug everything in here, right? If it's easier for you to think about, okay, out of this, I've got a length of 9, and I'm only looking at a half, so 1/2 out of 9. There's several ways to think about this, and whichever one kind of connects to you the most, then yeah, feel free to kind of approach it that way. Any other questions on that one before we keep going? All right, so got kind of the solution here. What if I make 9.5 pounds? What's the probability, and I won't ask this one on ivory, what's the probability that demand is exactly 9.5? I've made exactly the right amount. What did I say earlier about continuous random variables?
0, because it has to be.
Any one value, the probability is equal to 0. So I told you that, and you might think like, well, I don't really understand the 1/infinity thing and how the limited approach is 0. It also seems counterintuitive. So let's just use what we know about this uniform distribution, right? You can use that density function, or you can think about this as, if I want the probability of exactly 9.5, I'm wanting the area that's under the curve and in between my two values. But here, if I just want one value, my interval starts and stops at the same value. So if I try to plug 9.5 in here for both A and B, what happens? If I'm looking for the probability of any one value, I'm always going to end up with 0 in my numerator. 0 over anything is always 0, right? So it's not only like a mathematical principle that this probability of any one value, if it's truly continuous, would be 0, but it also plays out when we start using these density functions, right? Kind of supports the idea, okay? All right. Any other questions about the uniform distribution? We're going to kind of jump into the normal distribution here for a little bit today. So I'll go through this quick. I don't know. I used to think this was an interesting story, and it probably is, but I probably told it too many times. But there's this guy, right, Carl Gauss. Okay, so he was this really intelligent guy. He, back in the day, Renaissance man. Back then, if you were intelligent and educated, you basically did work in everything, right? Statistics, physics, everything. So he, basically discovered what we now call the normal distribution. Sometimes you'll hear it referred to as the Gaussian distribution, basically his last name. And then sometimes we'll refer to it as the bell curve, right? Because I've erased them all now, but when I had it drawn out earlier, right, it kind of looks like a bell. So when he was young, right, he was misbehaving. He was in grade school, and the teacher thought, how can I get this kid to settle down? He probably had ADHD or something. She's like, go over in the corner, add up the numbers from 1 to 100. I thought it was going to keep this kid busy. So he takes, she's thinking, okay, he's going to go 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. It's going to take him a while. He's going to calm himself down. He's a little kid. He's just misbehaving. Comes back in a matter of seconds, right, and has the correct answer. So how did he do this? And maybe this is something you can like trick some of your friends into thinking that like you're an ultra genius or something. Right? If I've got 1 to 100, what's 1 plus 100? It's not a trick question. 101. It's 2 plus 99. 101. It's 3 plus 98. 101. This continues all the way down until you get to 50 plus 51, which is 101. So you've got 50 pairs that add up to 101. So 50 times 101, 5,050. So you can basically, like, this was like a young kid figuring this out, right? But there's an actual formula, right? Not just based off intuition, or not you can do, which is if I want to take any values and add them up from 1 to not just 100, I can do 1 to 200. There's actually this formula would spit out at me what the correct answer is. But we can kind of think about that formula in our heads, right? We can just do these pairs, and every time I'm going down one, well, the next 2 numbers will add up to the same value, right? So I don't know, kind of interesting. Like I said, maybe use it on your friend, make some money. I don't know if you can't do it in like under 10 seconds or something. I probably should not be telling you to do this. This seems highly immoral, but you know, you gotta use your intelligence the best way you can. So we got this guy, he came up with this monumental discovery, which is the normal distribution, which is really the underpinning of almost everything we do in statistics, right? Or we will do for the rest of the semester. Excuse me. So it relies on kind of looking at these continuous random variables that take on these shapes that I've been kind of drawing earlier, which is we reference as kind of this bell curve. Okay? So what this bell curve is really telling us is that the values, if we were to kind of think about the middle value here, a normal distribution is symmetric. So the mean will always be equal to the median. Okay? So it's symmetric around this mean. And what it's telling us is that the probability of values near the mean is relatively high. But as we move in either direction, the probabilities taper off equally as we move, you know, further away from the mean above it and further away from the mean below it. Okay? So, you know, the reason why it was kind of a monumental story, it shows up everywhere in nature, right? So I think, yeah, so human height, rainfall, temperature. I'll show you a couple examples before we leave today. Where like in any, like almost all biological markers or biometrics or human performance, it almost always follows really close to a normal distribution, right? So it becomes this really important distribution for us to understand. Okay. Eventually, we'll get to how we can apply it to what we call regression, which if you're a finance major or you're wanting to, really, if you're any major, marketing, right? Understanding how to use linear regression is a significant tool to raise yourself above kind of everybody else, right? To kind of stand out from other you know, whatever position you want to be, right? Having that tool is really important. So we'll eventually get there. But first, you need to understand a little bit more about the normal distribution. Okay. So the normal distribution has its own density function, just like the uniform did, or the binomial, or SON. Don't write it down. It looks something like this. It's a mess. Right? I don't want to deal with this. Okay. You know, it's kind of interesting. We see it show up in nature and biology a lot. And notice it's got these two natural numbers. It's got E in it, and it also has pi. Right? So kind of seems, you know, a little bit happenstance. This is, you know, why I think sometimes mathematics is a little bit, I don't want to say spiritual, but like this is kind of bizarre, right? A little bit weird. So the other things in this distribution, well, we're just looking at different values for X. And then the only other things are the mean and the variance of this distribution. Okay. So we can have normally distributed variables, right? But if I looked at human height and then I looked at rainfall, what's going to be true? They're both measured in inches. But what's going to be true about the mean for human height relative to average rainfall, at the very least, average rainfall in Indiana? On average, people are like 68 inches tall, 67 inches tall. Do you think we get that much average rainfall? No, we don't even do that. So they can both be normally distributed, but their mean is different, right? So we already talked about the fact that it's symmetric. Talked about because of that, the mean will be equal to the median. But it's also going to be, we can have different normal distributions just defined differently by their mean and variance. So the mean, right, is going to do what to our distribution? If we have a normal distribution, and maybe it's even easier to think about. So here I've got human height, right? And I said its mean was like 68. So if we think about average or monthly rainfall, right, that follows a normal distribution, but it's probably going to have much lower mean. So if I was drawing that distribution out, what's going to happen if I draw it relative to human heights distribution? It's rainfall is normally distributed, but it just has a lower mean. I can't remember what exactly it is. I think every month it's something like 5 or 6 at the most, right? So that mean is just going to shift the normal distribution along the x-axis, right? So think about here, right? Different means, it's just going to shift my distribution along the x-axis. Okay. Any questions on that? That shouldn't be too terribly tough. All right, what if I have two distributions of different variance? So let's say I've got my first distribution got its mean, and I don't know, let's say its variance is 10. If I have another normally distributed variable that has the same mean, but the variance is a little bit higher, right? So let's say the second distribution has a variance of, I'll just make it way higher, 100. What's going to happen to my distribution? Same mean, the variance is now higher. We kind of talked about this a little bit before.
Is it gonna be more spread out in terms of its endpoints?
Right, it's more spread out, which means,
Flatter.
yep, which means the shape of this distribution, right, it's going to be flat, kind of squished down. Because being more spread out, what that's telling us in terms of a random variable is that the values near the mean have become less likely for us to see, and the values further from the mean have become more likely for us to see. So the variance of the distribution, as it gets higher, will flatten that distribution. If the variance gets lower, it starts to kind of peak that distribution up. So kind of a nice little visual here, right? As our variance gets higher and higher, it just kind of flattens out that distribution, making the values further from the mean more likely, making the values close to the mean less likely. So all these are normal distributions. They're all symmetric. They all look like bell curves. It's just that their shape is a little bit different because of the variance, right? It flattens or peaks it. And they might shift along the x-axis if their mean is different. Okay. So if I looked at human height and I broke it down by males, females, right? Which one of these has a higher mean? That should not be a yeah, right. You can kind of see like the male height distribution is shifted a little bit to the right. Which one of these has a higher variance?
I mean,
Yeah, so the higher variance flattens it. So which one's kind of shorter in a sense? Male height. So when you look at a lot of like biological markers, sometimes more often than not, the male kind of variable tends to be a little bit more spread out, a little bit more variation in male. And there's probably a biological reason. I'm not well versed enough in science to understand why. But right, we can see very clearly, at least if we graph out the distributions, there's a little more variation in male height than there is female height. And that's simply by looking at the height of these distributions. Okay? So, the normal distribution, we were using it earlier, the same thing applies as any continuous random variable. The area under that curve, the area under that distribution, that density function, is always going to be equal to 1. Okay? So this is like what we were doing before. We can start to break this down to different areas. Okay? Kind of a unique trait, right, is that if something follows a normal distribution, if we go out 1 standard deviation above the mean and 1 standard deviation below the mean, if we were trying to use that density function to find the probability we're in between those two values, it'll always be 68%, or probably 0.68. Okay? So, in practice, these would be a certain value. We could take average human height, go 1 standard deviation above and below that, use those two values, use the density function, integrate that function in between those, and we'll always end up with 0.68. Now, we won't do it today, but probably Wednesday, or at the very least next Monday, not Monday, we don't have class Monday, right? Next Wednesday, I'll kind of show you why this is. But for now, it's just an interesting property that comes out of it. If I go 2 standard deviations above and below, well, now I've just captured more of the possible values for X. If I go 2 standard deviations above and below, I'm at about 95% probability I'm somewhere in between those. If I go out 3 standard deviations, I'm up to like 99.7. So I don't know, have any of you heard or if you had a class where they reference 6 sigma? Anybody heard that before? So yeah, production process, usually you hear that, they'll use it a lot. Well, if we're already at 3 sigma here, right? 3 standard deviations, 6 sigma is really saying 6 standard deviations. So if at 3 standard deviations above and below the mean, we're at 99.7%, imagine at 6 sigma, we're like at 99.99999%. Right? That's kind of what they're referencing, making sure that they can almost guarantee that you're going to be within, 6 standard deviations above and below. Okay? Questions? I mean, sure there's questions on this, because I haven't shown you exactly why this holds up, but hopefully it's the next class or the next Wednesday, I'll revisit this idea and show you exactly why that's the case. So we're going to start writing out these different normally distributed variables. And we'll kind of use still that capital X, right, to represent a random variable. But we'll say it's distributed normally, using just kind of that capital N, and then give its mean and its variance. That's typically how we'll write out a normally distributed variable. We have a special case, which not loving where we're gonna X. I would love to go a little more into it today. With 10 minutes left, I probably won't get to show you too much of how we use those tables, but I will have to reference those before we leave. So a standard normal distribution would be a normal distribution where the mean is 0 and the variance is 1. We'll call that a standard normal distribution. Okay? So what's a unique property about the standard normal distribution is if the variance is 1, what's the standard deviation?
1.
Yeah, square root of the variance, so the square root of 1 is just 1. Right? So it's really the only normal distribution where the variance and the standard deviation can be the same. Right? So we'll use this a lot because if we look at the standard normal distribution, okay, what this value is actually, whatever X value we're looking at, what that would really represent is the number of standard deviations away from the mean that value is. Okay? So I'll try to give you a little support behind why. So I've got kind of my standard normal distribution. And when I'll start calling these, instead of referencing it as like an X variable for a standard normal distribution, we'll start referencing these as Z values. Okay? So these Z values tell us how many standard deviations away from the mean we are. So if I were to be looking at a standard normal distribution and the Z value I see is 2, that's telling me that I'm 2 standard deviations above the mean, right? Because the standard deviation is 1, so the value of 2 is 2 standard deviations above the mean, right? The standard deviation is just 1. And if I were to think about, well, what if I saw like negative 3.5? That Z value is really just representing 3.5 standard deviations below the mean. Okay? So if I could somehow take a regular, variable X that's normally distributed, and I could convert it into a standard normal distribution, well, then I could start to do things like, okay, the average, average height in the US or something is, 67 inches. I can calculate the standard deviation. I could then say, okay, how many standard deviations away from that mean is, 73 inches. So if I can take that value of 73 and convert it into a Z-score, that would tell me how many standard deviations above the mean that value of 73 was. So we're going to start out with these normally distributed variables, and we're going to convert them into a standard normal distribution. Because once we convert them into a standard normal distribution, those Z-scores kind of tell us how many standard deviations away we are, which starts to kind of relate to this, right? Being 1 to the standard deviation above or below, the probability will always be 0.68. Between 3 standard deviations, 0.997. So let me skip forward here a little bit. We'll kind of revisit this next class. I got a couple things I think are interesting. Okay. So for one, we'll talk about how these tables work next class, but I have a file up on Canvas. It's called Z tables, which are really a Z table or standard normal tables. Starting on Wednesday, I'll expect that you have those in front of you. I can show them to you on the screen, but it's going to be really small, right? So to avoid you having to look at the screen and squint and try to answer ICRO questions or try to follow along with me, I would highly suggest that you print it out and bring it to you with class from here on out. Or if you bring your computers, you can obviously pull the file up from Canvas, but I also think it just helps to kind of have that in front of you as an actual hard copy. But either way, whether or not you print it out or have it on your computer in front of you, I will expect that in class you have that from here on out. Okay. So make sure you do that before we start class on Wednesday as well. So you got that Learn Smart, and you should print this out or make sure that you're able to kind of have this in front of you. Okay. We're not quite, almost done. Okay. So I think I have a couple pictures that I think are interesting. Here we go. So I'm telling you that this pops up a lot, right? But maybe I can want to kind of prove this to you. Right? So I got a couple examples I think are good, normal distribution examples. So here's human height. So even if I just lump kind of genders together, this still doesn't even look bimodal. It's a pretty nice normal distribution, right? Not perfect. So this one I really geeked out about. I saw this on Instagram, and I think they were posting it, and like the caption said, like, "Are you in the 99th percentile?" It was some CrossFit workout. So they had all these reps that the people were doing. I don't know what they equate to or what the workout was or whatever, but I mean, look at the distribution of at least female performance in whatever event this was. It is as close to a normal distribution as you can possibly get. I mean, in that, naturally. So, we see it pop up, like I said, in human performance, biological markers like human height, and the males was pretty close to normal distribution. Had a little weird thing going on here. I don't know, what the workout was. Maybe there was a reason why. The other one that I found kind of interesting. So I pulled this data set, and this I think is speaks to broader, more broader discussion of how do we use statistics to tell accurate stories. Right? So I've always had this idea that, men and women or males, females, whatever, probably have similar strength. If we had exactly the same amount of muscle tissues, there's no reason to believe that anyone's muscle tissues work any differently. The problem is if I use something like powerlifting data, right? So I chose this one power lift, which is the deadlift, right? So how much weight did the individuals lift? I had like tons of meat, like thousands of different meats, which, however many people were in each meet, that's, how many observations I had. So a ton, it was over a couple 100,000. So I kind of did a quick histogram, and you can kind of see, okay, the average of pretty close to a normal distribution. There's a little bit of a right skew here, but we can explain that away in that people who are doing these competitions, it's probably more likely that people who are good are going to join up and do it. The people who are bad just don't go, right? So the left tail probably exists. They're just not actually lifting at the meet, right? If we could force everybody to compete, then we would probably have a real nice normal distribution. Okay? And if we look at the averages here, I would say the males is somewhere in between 500-600. Female weight lifted, I would guess somewhere around 300 kilograms, right? So you might look at this and be like, well, okay, your idea is stupid. Obviously, males are way stronger, right? But I'm going to tell you, after looking at that data set, there's a lot more 400-pound men in that data set than there were 400-pound women, right? So if we don't factor in the fact that men are typically heavier, which would then mean you could probably lift more weight, right? Then yeah, we'll come to some ridiculous conclusion that doesn't really, we're not actually getting at what we're interested in. So we might want to do something like weight lifted per pound of body weight, right? So they have a measure that they come up with this in powerlifting. It's called the Wilks. So it's basically, if it's easier for you to think about, it's the amount of weight lifted divided by the weight of the individual. So I looked at the distribution of that. This is even more of a nice normal distribution. Once again, a little bit of a right tail issue because the people that on the left tail just don't compete. Now, if we look at these averages, I'm kind of just below 400 here, maybe 370, 380. And here, I'm just below 400 as well. Right? If I actually compare those means, there's other statistical tests we can do. And I actually couldn't find with any statistical power that there's actually any difference when I factor in kind of the per pound strength of lifters. So I don't know, I thought this is kind of an interesting example, even if you're not interested in like weightlifting or anything like that. Like it is a general like conclusion that someone could come up to you with. Like, oh yeah, men are way stronger than women. You're like, okay, yeah, but you're ignoring a lot of other factors, right? If you account for one factor, which is human body weight, we actually get that there's absolutely no difference in strength potential. And you can factor in more things. Like I'm sure if we could factor in human height here, it'd become even less of a difference. I don't know. I thought it was kind of an interesting way. It's going to use statistics. I had a bunch of normal distributions laying around, so it fit in with our discussion. And yeah, so we'll kind of end it there. We'll pick back up with the normal distribution. Get that Learn Smart done before class on Wednesday. Print that standard normal Z table out. And I will see you guys on Wednesday.